Okay, now let's take a look at this problem for a combination of both elasticity and the balance of a structure. These are the two subjects for the chapter. First part being equilibrium, second part being elasticity, and this problem combines both aspects. So what we have here is a heavy beam, heavy uniform beam of length L. It starts from point A and ends at point C. Now it is pivoted at point A, so there is a pivoting force here at point A. It's also being supported by a post at point B, which also happens to be the center of mass of the beam in the middle. And then on top of that, there is a cable that's connected to point C, the other end of the beam, to provide an upward supporting force. Okay, it says that when the cable and the post are both in their at their equilibrium lengths, which means they're neither being stretched or compressed, the beam is at angle theta from horizontal. Okay, now when you let go of the beam, the weight of the beam is gonna push it down a little bit, so it's gonna compress the post. At the same time, it's gonna stretch the cable, and as a result, the angle theta has been decreased by a very small amount, delta. Okay, so there's compression and stretch for the post and the cable, but not by much. Okay, and given that information, you want to find the weight of the beam and the supporting force F at its pivot point A. All right, now we can find the force of support at the post and also the force support at the cable. If we know these forces, then we can also figure out the amount of stretch they have, or given the amount of stretch, we can figure out how much supporting force each would provide. Okay, and the net force on the beam has to be equal to 0, along with net torque. Now, one thing we notice is that the weight of the beam at point B and the force of the support at point B by the post, as well as the supporting force provided by the cable at point C, all these forces are vertical. Okay, there is no horizontal force at these positions, points B and C, and therefore at point A, the net force, the supporting force at point A has to be in the vertical direction as well. Otherwise, you have a net horizontal force, and that's not allowed. So the force F, the supporting force at point A, must be vertical. Okay, I don't know what it is, but we do know it's vertical. So let me label that. There's a supporting force F here, which is what you need to find out. Now, the beam has its own weight at point B, and we call this mg, m being the mass. Okay, and there's a supporting force provided by the post, which I call, what do we call it? F1. Okay, there's also supporting force from the cable, which call F2. Now, F1 and F2 depends on how much the post and the cable deform. That is how much they're being compressed, the post being compressed, and how much the cable is being stretched. And we have information to work that out. How do we work that out? We look at how much the post has been compressed. Okay, without any compression, the angle the beam makes with the horizontal is theta. Now, as the beam gets compressed, the angle theta changes by a small amount. The amount is delta, and from delta and the length of the beam, I can find the amount of compression of the post, and that's done with a simple geometrical consideration. Let's see how we can do that. Okay, if you draw a little triangle like this, from point A to point B, this angle originally is theta, and this length from A to B is half of L. Okay, now this length would be the original length of the post when the angle equals theta, right? Original length of the post, why don't we call it L1? Okay, now I want to know how much L1 changes when the angle theta decreases by an amount delta. Okay, let's see. Now L1 equals to what? Half of L times sine theta, right? half L times sine theta. I'm looking for the change to L1, which has to do with the change in angle theta. And so basically, what I want to find is that when sine theta changes, when theta changes by a very small amount delta, how much is the change in L1? We call delta L1. Delta L1. What is that equal to? Well, that is, I can take a derivative of both sides, okay, and then so basically d theta of L over 2 sine theta, and then delta theta. Delta theta, that's the change in theta, we simply call it delta. Okay, delta L1 is actually negative because clearly the pulse is being compressed, so delta L is negative. And I don't care about that. I just care about the absolute value here. So I'm going to keep the right-hand side also positive. Okay, now when you do that, you work out the derivative, you can easily get L over 2 cosine theta and times delta. Okay, that is the amount of compression of the post. And if you know also the cross-section area of the post, of course, that has to be given. And the Young's modulus, then I can find the amount of supporting force F1. Okay, that's from the second part of this chapter. So F1 would have to be equal to what? 1 over the Young's modulus, actually the Young's modulus, Y1, okay, assuming the post, I'm label it, everything labeled 1, and its cable, everything labeled 2. The cable length, we call it L2. Okay, so what is F1 equal to? F1 equals to the Young's modulus, and then times the amount of stretch, the delta L1, the absolute value, divided by its original length. Okay. And don't forget, the value of F1 also has to do with how thick the cable is. The thicker it is, the greater the force F1. So it has to do with area A1, the cross-section area A1. These are all given. Okay, so we can then plug in the value of delta L1, then I can get the full expression for F1. So just Y1, A1 over L1 times this expression here, which is L over 2 cosine theta times delta. Okay, so this is this whole set of constants times delta. That's F1. Okay, with the same idea, I can find F2. Okay, in this case, the cable is being stretched by a certain amount. Now, how much is the cable stretched? Well, you don't have to start from scratch. You notice that as the beam goes down by changing the angle theta by a small amount, both points B and C will go down. But since C is it's twice as far from point A compared with point B, C will go down twice as much. Okay, you can examine this same triangle here, except you replace L over 2 with L because you're going from A to C instead of from A to B. Okay, so the amount of stretch for the cable is just twice as much as delta L1. So delta L2 is twice as much delta L1. And that tells me immediately how to find F2. F2 equals to Y2. Okay. And then delta L2, which we know is positive. We don't have to take the absolute value. Divided by L2 times A2. Okay. And I can plug in the expression of delta L2. We know that delta L2 is 2 times absolute value of delta L1. So we plug that in, I get Y2, A2. A2 is the cross-section area of the cable, and then L2. And then there's no factor of 2 in the denominator anymore here. It's just L cosine theta. And times delta. Okay, times delta. So we found F1 and F2. All these are given. Given these forces, F1 and F2, how does one find the mass M and the supporting force? Well, we can find there's a connection with all these forces. I know the net force has to be 0 in the vertical direction, where it now is horizontal direction is 0. So the sum of the force in the y direction has to be equal to 0, which means F that's upward, okay, plus F1, right? And then plus F2. F2 is the force from the cable. That has equal to mg. Mg is the only downward force. Okay, now of course, that doesn't solve the problem just yet because I don't know what F is, I don't know what M is. I mean, they do tell you the symbol of the mass of the beam is M, but they're looking for the weight of the beam. So that is telling me that they don't know what the mass is, even though we call it M, okay? So we have to find that out. So that is one equation, but it doesn't solve the problem yet. So how do you find another equation? Well, we use the net torque equal to 0, okay? You can apply this to any points, A, B, C, whatever point you want. But since we don't know what the force F1 is, F is, I'm sorry, then why don't I set the reference point for the torque at point A, therefore I wouldn't have F in the equation of the torque being equal to 0 around point A. That makes my job easier. Okay, so I'm gonna set the net torque equal to 0 at point A, okay? And let's see what I get. All right, now there are a couple of counterclockwise torques, one from F1, the other from F2. So it's gonna be F1 times its lever arm, which is L/2 cosine theta. That's the lever arm, L/2 cosine theta. Now you say, wait, it's not theta, it's theta minus delta, right? Sure, but delta is extremely small, okay? So when you write cosine theta, it's not that different from cosine of theta minus delta, so we can just ignore the delta in that case. Okay, and that is a counterclockwise torque, plus the force, the torque provided by F2, which is also counterclockwise, and that is F2 times, this time it's L cosine theta, not half of L cosine theta, okay? Both are clockwise torques, counterclockwise torques, and that equals to the torque provided by the weight of the beam, which is mg times L/2 cosine theta, right? So now we have two equations, right? Equation number 1 and equation number 2, and what are we looking for? We're looking for F, and we're looking for M, or mg, whatever you call it, W, which is equal to mg. Okay, and then you can finish the algebra very easily. Right into what F1 is, what F2 is. Just plug in the value of F1 and F2 into equation number 1 and equation number 2. You can solve for everything else. So this is an interesting problem because it combines both elasticity and structural balance. And that happens in real life when you design a structure and you support the structure with posts and cables. You have to consider both the elasticity and the balance of force and torque.